We have been talking about Raft, and the goal of Raft is to provide safety, which is defined as linearizability for us, and provide liveness. As long as f plus one workers are able to talk to each other in a 2f+1 replica system, the system should continue to make progress. That is, accept reads and writes. So we have talked about election safety, right? But the high level goal was not election safety, right? So we have been talking about replicated state machines. So the same state machine is replicated across replicas, and we are trying to get state machine safety. That is, if I have applied a certain update on a certain log index, then every replica must apply the same value at the same log index, right? So leader election is good, but can leader election have issues with this, right? So we, at the end, we want this state machine safety, but it may be, can it be possible that I miss committed entries while I'm replacing the leaders, right? So let us see that, let us say this was our log, right? So what I'm writing here is, this is the log index 1 2 3, right? But inside each entry I'm just writing the term number, right? So let us say S1 was the leader for term 1, right? So it is accepting whatever operations it wants to accept for term 1, right? It is writing those operations in the log. So it replicated 3 entries on S1 and S2. So these 3 entries could be committed entries, right? Because they are replicated on a majority. And S3 was rebooting after receiving 1 entry, right? And then let us say S1 crashes. So far S3 is allowed to become the leader for term 2, right? So let us say S3's election timer expires first. So S3 will become a candidate, ask for votes, S2 will give it vote, and S3 becomes the leader, right? So then it will start accepting entries for term 2, right? So this is a problem. We don't want this to happen, right? So we want another property that the paper calls leader completeness. So what this says is, only replicas which have all the committed entries, only they should be allowed to become a leader, right? S3 should not become a leader because S3 did not have all the committed entries. Only S2 should be able to become a leader for term 2 because S2 has all the committed entries. And the general mechanism we will follow is that when S3 asks for votes from S2, S2 will not give it votes, right? Somehow. So S2 will try to realize that S3 does not have all the committed entries, so I should not give it votes, right? Okay, so how to do this? Any thoughts? Right. Right. So one approach is, I will, when I request for votes, I will also tell you the log length, right? I will tell you how many log entries I have, and if I have more logs than you, then you give me votes. But if I have more logs than you, then like you only give votes if you have shorter log, right? Any issues with this?
So basically, it has to be committed first, and then we can proceed further. So we could have some kind
No, issues with this algorithm. Before you give new algorithm, what is the issue with this algorithm? Or is there a issue with this
We need
algorithm?
to always wait for committing. So there could be an overhead on that.
We need to have exact the same state that the previous leader had, right? All the logs. So if both the candidates miss like two messages, two different messages, say. So both of them have the same length, but none of them are complete.
No, it could be that S3, like right now in this diagram you have S3 1 and 2, right? Maybe there's another message that in the meantime also reached S3, so it became 1, 2, 2. So the log length of
No, this is assuming 2 became the leader. S3 became the leader for term 2. We are saying S3 should not even become a leader, right? So we are trying to design a mechanism to get this leader completeness.
Since replicas will apply the logs, the length may decrease over time.
Okay, so far we are not pruning logs, right? So logs are this infinite sequence, right? We have not talked about pruning logs.
We can have a machine becoming leader if we have large enough machines that has less number of logs than majority. Because both the candidate have less number of logs, then the better one wins.
Right, so it's a possibility that it doesn't guarantee that the replica with maximum log length wins. That's your problem. Okay. Yeah, but that is actually not a problem, as we will see going forward. But there is a problem with this algorithm. So let us say S3 got S3 got all the term 1's requests, right? And let us say it became leader for term. So and then S1 crashes, right? So now S2 and S3 have identical logs. So now S3 can become a leader, right? So it got some accepted some requests in term 2, and then it got partitioned, right? So it is not able to replicate these requests to S2, right? And S1 has restarted in the meantime, right? So S1 also is not receiving any heartbeats, so it or let us say S2 has not been receiving heartbeats, so S2 starts another election, right? And it becomes the leader for term 3, right? Because S1 and S2 have identical logs. So it accepts some requests for term 3, right? So far so good. And now S2 crashes. So we have to elect a leader for term 4 now, but this 3 is a committed entry, right? Because 3 was replicated on majority. These 2's are not committed entries, but S3 ended up having longer logs than S1, right? So our leader completeness property says you should only allow someone to become a leader if they have all the committed entries, right? So in this case, if I'm just voting based on log length, then S3 will end up becoming leader when S3 did not have a committed entry. Okay, so log length didn't work. Any other suggestions?
Kind of improvement.
Last committed time.
You can have like a centralized logging server separate.
Who will make so centralized logging server? But who will make that fault tolerant?
So every worker would like catch their part. That would
Yeah, to think about it.
So I was thinking of a C certificate and P certificate. That would be having that dependency. Committing thing would be more on that. There won't be too much overhead.
Wait, let's not complete. Let's just answer the question, right? Who should go give votes to whom, and how to decide that I can give a vote? So one solution we might come up with is maybe we might want to use committed index, right? So remember when the leader can form a majority, right? It responds to the client, and in the next append entries or in the next heartbeat, it also tells what is the commit index, right? So it can tell, so when S2 is able to commit 3, it will tell S1 that commit index is 4, right? So S1 is free to commit everything till log entry 4, right? But S3, from the point of view of S3, commit index is only 3, right? So S1 cannot vote for S3 because the commit index that S1 knows is higher than commit index of what S3 knows, right? Does this work?
Let me explain it again.
So remember the way we are committing, right? So we have S1 and S2, S3, right? So S2 is leader for term 3, so it received a request from client, right? It appended it in the log, right? It sent it to S1. S1 said, okay, I have also appended it in log, right? So first the request came, then S2 added it in its log, then it sent append entries to S1. S1 appended in its log and sent OK to S2. Then S2 can say that your write is complete because I found a majority. And then a later append entries request, I will tell that by the way commit index is 4. Right. So when S1 sees that the commit index is 4, then it can apply this log in its state machine. Right. So before it sees the commit index 3, this log entry is just pending. It is just sitting, but we have not actually applied it to the state machine. Right.
If between step 6 and 7 there is a network failure, then
Right. So it is a possibility that S2 told the client that your request is committed and then it crashed. Right. So 7 actually never happened. So the commit index of S1 is still 3. Right. But to the client, we have guaranteed to the client that 3 is actually a committed entry. We told the client that 3 is a committed entry, but the commit index of S1 and S3 are identical. So how to, any solutions? Okay, so the solution that Raft gives is I am more caught up, right? If my term number, right, for my last log entry
can you not use just timestamp? Like when you're like when you're saving a log, just save like when you're sending a log, like the leader sends the time at which it received the request, and like use like the one that has the latest timestamp, the log with the latest timestamp, that one.
So timestamp is not required, right? Timestamp is already captured in term number plus log index, right? Okay, so the solution is that I can give votes or I can receive votes if my term number is greater than your term number for last log entry, and if they are equal, then my log length is greater than your log length. Right. So at the time of requesting votes, a candidate will send. So let us say this is our candidate 1113, and this was S1, this one was S3. Right. So it will send the last term number, which is 3. It will also send the log length. Right. So when S1 is requesting for votes, it will send that my last term number is 3 and the length of my log is 4. So S3 will check that the last log, that the term number is actually higher. So S3 can give votes to S1. But when S3 asks for vote, it will not receive votes because its last term number is lower. If it was like this, then S3 would have received votes, but S1 would not have received votes from S3. Right? So the last term number is the same, but the length, the log is longer. Okay, so let's play with this a little bit and convince ourselves of its correctness. Right? So this sounds pretty. We don't know yet if it is correct. Right? So let's convince ourselves. Okay, let us say this is the state of the system, right? We have 6 replicas A, B, C, D, E, F, and this is their logs. The number inside a box represents the term number, right? And we have the log. So first of all, let's discuss which of these can be committed entries. This can be a committed entry because it is on majority, right? This can also be committed because it is on majority. These can be committed and these can be committed, right? The rest, for instance, this, they are not committed entries, right? Because they cannot be committed because they are not on majority. Yeah, so it's fine. Yeah, generally you will have odd number of machine 2f plus 1, but this is even. So how did this execution happen? Let us say someone was leader for term 1, right? They replicated 3 entries across all the replicas, then the leader crashed. Then F became leader for term 2, right? Because it can get votes from everyone, right? But it is unable to append entries for some reason, right? And then it restarts. In the meantime, everyone else is trying to do an election, and F also does an election for term 3 and ends up winning the election. So F becomes leader for term 3, but it is again not able to append its entries, and then F just dies. Next, E becomes the leader for term 4 because everyone else has same logs till term 1. So E becomes leader, it replicates one entry to B, B crashed after that. Then it replicates another entry to A, C and D, and then E crashed, and then E is not able to send its entries and it dies, and so on. Right, so let's try to reason about who can become a leader. So we are in this state, right, and who can become a leader in term 8, right? So we want to do elections for term 8, and our leader completeness property says that the leader must have all committed entries. Right, so we have already identified that these circled ones are the only committed entries, right? So let us see who can become leader in this setup. Okay, can B vote for A? B can vote for A, right? Can C vote for A? No, right? D can also not vote for A. E can vote for A, and F can vote for A, right? So A can potentially receive 4 votes. So A can become a leader, right? A will not vote for B, C will not vote for B, D will not vote for B, E will also not vote for B, F can vote for B, right? So B could only receive 2 votes, so it cannot become a leader. For C, everyone except D can vote for C, right? So C can become a leader. Everyone can vote for D because it is the only one that has seen 7th term, right? So D can become a leader. Only F, E and B are able to vote for F. Sorry, B and F are able to vote for E. So it is not able to form majority. So E can also not become a leader. And F, no one votes for F. So F can also not become a leader. So we can see that the only replicas who became leaders have all the committed entries, right? Right. This algorithm ensures that only if you have the committed entries, only then you can become the leader. Right. So it's not a formal proof. I think some of us may still be a little unsatisfied. But you can think about it some more, right? But this should give us some convincing argument that only if you have all the committed entries, only then you can become the leader. Okay, so now, okay, any questions?
Who was the leader for term 5?
Any of these could have been leaders, A, C, or D. Okay, so now let us say someone became a leader, but we end up with diverging logs, right? So this guy thinks the logs are this, right? This guy thinks the logs are this, right? So everyone ends up with diverging logs. So what to do about diverging logs, right? So because of leader completeness property, the leader has all the committed entries, right? So leader can force its logs on others, right? So basically, let us say this became the leader for term 8. It will force its log. It will remove 4 and put 5. Remove 4, put 5, right? Put 6, 6, 6, 7, 7, right? It will force its log on all the diverging logs, right? And the way it will do it is when it has a append entry request for term 8, it will additionally send the last value for the previous log index. That for the previous log index, the term should be 7. Only then you should accept this new log entry, right? So let us say it sends this to F. F says I don't have 7 in my log. So then it will have to walk back. Then it will say, do you have 7 here? Then it will again reject and keep walking back until it gets here, right? So at this point, F will accept this 4 because the previous log entry matches, right? And then D can play the log forward to force its log on top of F. So this should make us a bit uncomfortable. Like we are deleting other people's logs. Do we still have state machine safety property? State machine safety says, I mean, this can be pretty risky, right? What if this 2 was applied already to the state machine, right? If F had already applied this 2 to the state machine, and then I come and change the log, then we might have a problem, right? Because the state machine safety property says once I have applied a entry, everyone should apply the same entry, right? So why is forcing this log okay?
You can also force the state machine after that.
Right. So the other option is we can also force the state machine after becoming the leader. Yeah, that's also okay. So basically, if this log is growing long, then periodically we can also, so we have not talked about pruning the log, but basically we can create a snapshot, right? So let us say I created a snapshot at this point, right? And then I prune all the logs. So I create a snapshot and then keep the rest of the logs. So then I don't have to walk back all the way till the beginning of time, right? I can send over the snapshot and then play the rest of the log, right? So periodically we will prune the log by creating snapshot. So we can only prune the committed entries, right? If there are pending entries, they cannot be pruned. Why can the pending entries not be pruned? Yeah, so they are not committed, so they are not reflected in the state machine, right? So they are not part of the snapshot, right? So everything that is committed is part of the snapshot.
Entries can be committed, but like still they may not be replicated because if between 6 and 7 the network fails, so they are committed in the view of the leader, but they are not replicated.
Right. So right. So when I'm catching up followers, I will send the snapshot and the log, right? So they will first, so when they get the snapshot, they are logically at this point in the log already by receiving this snapshot, and then they can play rest of the log, right? Okay, so the trouble is we forced our logs on others, right? And but what if they had already committed in the entry that we have deleted in the local state machine, right? So the issue is uh, let me see. Right, so the issue is, let us say S1 became the leader for term 3. It is going to force this 3 on top of S2, right? But if S2 has already applied this log in its local state machine, then we have a problem, right? What to do with the state machine, because it had already applied this 2. So the insight is, can this be a committed entry, right? So this 2, if 2 is committed entry, then we have a problem, right? So let us say 2 is a committed entry. So if 2 is a committed entry, it must be on majority of replicas, right? If 2 is a committed entry, it must be on the majority of replicas. But if it was on majority of replicas, then how did S1 become leader? Right? Because when S1 asked for vote for term 3, it will send its last term index as term 1. Right? So it will only receive votes from S5. It will not receive votes from S2, S3 and S4. Right? So we again have the same argument that you cannot have two majorities. Right? So there will be someone to break the tie. Right? If 2 was a committed entry, then it must have been on the majority of replicas. If it was on majority of replicas, then S1 cannot become leader for term 3. So therefore we are okay to force our logs because we are sure that this 2 is not a committed entry. It's quite subtle. Okay, any questions? Okay, so the other thing is when we are forcing our log onto others, we are only checking the last log index, right? Why are we not checking the entire log, whether the entire log is the same, right? So can such things happen? So let us say, right? So S1 thinks the log is this, S2 thinks log is this. And S4 is, so S4 adds an entry into S1 because it only checked the last log in, value in the previous log entry is the same, but actually the value in somewhere else was different. Can this happen? Right, so when S3 is forcing its log, it is just checking, or actually during any append entries, it is just checking where the last log matches. If it doesn't match, then it will go back and make sure it matches.
The leader for term 3 would have changed instead.
Yeah, so it's just an inductive argument, right? So when the logs are empty, then logs trivially match. And whenever you are adding a new entry, you're making sure the previous entry was matching, right? So this 3 cannot be added. This 3 cannot be added in both the places because the entry before this 3 does not match. Okay, so overall, any questions? Okay, so this is a pretty complex algorithm, right? And it's very easy to get lost in the complexity, and it is reasonably so, right? The job that this algorithm is trying to do is quite difficult, right? If you think about it, right? We are trying to replicate a deterministic state machine across replicas, right, where anyone can crash at any time, and at the same time we are trying to maintain safety, right, which is expressed as linearizability, and we are also trying to maintain liveness, right? So we achieve state machine safety by achieving smaller properties like leader completeness, election safety, and so on. Right. Okay, so this completes our discussion on Raft. Any questions? Yeah.
Follower receives a log, does it like apply that to the state machine immediately?
No. So follower, so some entries in the log may be pending, right? So here these entries are pending. These cannot be applied to the log until the commit index increases to this point, right? So followers, so everyone is waiting for commit index to increase, right? So when the commit index increases, only then a log entry is applied to the state machine, right? But some entries may remain pending, and they may actually be overwritten by a leader, right? Because leader is forcing its log onto followers, right? So it is unsafe to apply this entry because it may change, right? Only the committed entries can be applied.
What is the mechanism to deal with the lost logs? Like there are some logs which are not committed, but still they can be valid entries.
So the question is, some logs are lost. Why are they lost?
Let's say logs written in term 2 or 3, they are not committed because they are not on majority, but after D is selected for terminate, these logs are lost. So is there any way where we could recover, because
Right.
these logs are valid logs?
Yeah. So we are feeling uncomfortable that all these logs are lost, right? But this is actually okay because F did not say yes to the client, right? So from the client's point of view, actually this, yeah. So client will retry, right? So from the client's
So
But
then we
client would have been told, I mean, the commit happens after it has told okay to the client, right?
no. So so we wait for receiving an acknowledgement from a majority, and then we say okay to the client.
Yeah, answers my question.
But it is written to the log after we have told okay to the client.
No. So yeah. So there are three things going on. So we have the log, right? Things are put into the log as soon as you receive from the client, but they are still not committed, right? So the commit index is still pointing to a location before the log entry,
The last log entry.
huh?
The last.
To wherever it is. Then you will say here are some logs to the followers. Then followers will say, okay, now I have appended the logs into my log. And then you can increment the commit index, right? So let us say this entry was actually replicated on majority of followers. Then you increment the commit index locally. And then you tell the client, okay, your request is done. Then it will tell the commit index to all the followers that the commit index is now 8. So everyone is, while of course doing this forcing logs and right. So uh, a follower can apply all the logs until this commit index. But basically in logs there are some pending entries, right, which are not applied to the state machine,
Which are not get committed.
which are not yet committed.
So from like a client's perspective, you want to maintain like a free for all messages, like whichever request I send first, I want that to be done first. That would be pretty slow, considering that I would have to wait every time to get like a commit request.
Right. So this is the problem, right? Consistency comes at a cost that we cannot, client has to wait until the until the leader has replicated the log on a majority, right? So actually these writes can be slow, right? And all these writes are actually going to the disk, right? Because we don't want to lose the log, right? Similar to write ahead logging. So everyone is acknowledging to the leader after writing the log to its own disk, right? So consistency comes with the overhead. So this is a good thing. So we will talk about this exact problem at 3 p.m.
So when is the when is the v value returned to the state after when the commit index is increased, then
Yeah. So if the commit index comes here, this replica is free to apply all these entries one at a time to the state machine.
they were already applied now before the entries before.
So right. So a replica will also remember what it has applied so far. So it will remember last applied. Right. So let us say it had applied nothing. So last applied is 0. Then commit index increased to 3. So it will apply 3 entries into its state machine and remember that I have applied 3 entries so far. Then it receives that, by the way, commit index is now 7. So it can apply the rest of the 4 entries and increment last applied to 7. Right. So every replica can independently play the log as soon as the commit index is increased. Okay, any other thoughts? Okay, so this paper won a best paper award at ATC. I highly recommend, like, you should enjoy this paper uh, if systems is for you. If you didn't enjoy this paper, then yeah, like, this is one of my favorite papers. So it takes a while to understand, but once you understand, you really see that it is quite beautiful.